Welcome everyone again. Now we are going to start with the cryptography today. Now, what is the cryptography? But before the cryptography, we are going to start with the camera, of course. So, one of the earliest the scientists, or actually he is a commander, which is Julio Cesar, which is a commander of France, and once he tried to send a message to his soldiers, and he tried to keep it a secret, and only his soldier should understand from this nonsense letters, let's say. So what he made the messages a secret by shifting each letter 3 letters forward in the alphabet. For example, sending the last 3 letters of the alphabet to the first 3, which is here. Actually, it is seen here. The mode 26 is the number of the alphabet, number of the letters in alphabet. So he uses just shifting the letters, the number of the letters actually. So for example, replace A by 0 if you just start with the 0, which is the index 1, 0, 1, 2, 3, 4, and it goes on, which is A, B, C, D, E, and it goes on to. So here, if you see 0, it means that it is 1. This is A. If you see 1, it means that it is B. If you see that it is 2, it means it is C. So the Cesar's encryption method, actually here we have a specific term, which is the encryption. So what encryption is? The encryption means when you, let me draw here, when you send a message, let's say this is the original message to the box. As you know, this is a very important box, and as an output it will be a secret message. In order to make the original message to the secret message, it means that encryption. If you try to, this is our first important term, which is encryption. So we are going to use that E in our further steps, and the process of making a message a secret. Now this is encryption as it is seen here. So what he did, Julio Cesar's logic, what we should do, for example, here with this one, what is the secret message produced from the message? Meet you in the park, using the Cesar's cipher method. So now we are going to make it a secret. So at first we are going to rewrite these letters. Meet me in the park. So if we use the as a 1, and if z is equals to 26, so we are going to make it as, for example, what is the B in our letters? The number of the B is 13. Number of E is 5 and 5. And what is T? T equals 20. And what is M? M is 13, is 5. And I means it is 9. We are looking here. We are checking which one is, or which letter has which number. Was for example, n has 14, and t is 20, h is 8, and e is 5, and p equals 16, a is 1. You can say it is 0, 1. It will be better to write 0, 5 or 0, 1, because in order not to confuse which is 15 or which is uh, 11 or which is 12, it might be some confusion. So it is 18 and k equals 11. So yes, if we just shift this one as a 3, it means that we are going to use as 16 instead of the m, and instead of the e, we are going to use 8. Instead of the e, we are going to use 8, and instead of t, we are going to use 23. And it is the same logic, the same process we are going to use for these two. And this will be a 23, and this will be, this h is 0h. At first h, we are going to make it will be 11, and now this will be 05, and it will be 08. Now it will be 16, it will be 19, and 01 will be 04, 18 it will be 21, and 11 it will be 14. Now what is the 16? It is p. And what is 8, which is h, which is the same, it is h, and 23, it is w. Now, what is the 16? Again, it is p. What is the 8? It is h. What is 12? It is l. What is the 17? It is q. And what is 23? Is w. 11 and 8 is h, yes. And what is 19 is s. D, 21, which is u, and 14, it is n. Yes, Oz, you are right. So now it is the secret message that Julio Caesar sent his troops or his soldiers, but the soldiers know how to decrypt this message. Now we are going to see what the decryption is actually. Now it is decrypt. As you remember that if there is a box, you are going to use the original message, you send the original message to the box, and if it is the output is the secret message, this calls as encryption. But if you send the message to the box, and output of this box will be original message, which we call as decryption. So it is important. Now we are going to use E as encryption and D for decryption. Okay, do not forget this one because it is important. Now we are going to use it. So now we are going to try to decrypt that ciphered text that was encrypted with the shift cipher with the shift, which is the K7, which means in this example we sent a message, which means we used just previous, as you see here, P equals, this one is the K, okay, and it uses as K plus or P plus 7. So in our example here, it means that P plus 7 is used instead of k equals to 7. So we are going to use that. For example, what is L is 12. So we are going to make it 12 minus 7, which will be 0.5, and which is the E. Okay, we are going to use that one. Or what is the K? K means that here in our previous slide, we are here to F P equals a function P plus 3 and mod 26. And this 3 is the K. So if the K equals 7, in order to use the encryption of this text, we have to use -7 in order to decrypt. Did you understand? That's great. So, Alams, you are asking for if we had Z, which it 26, what can we use for 29? As you see here, you have to use a mod 26. What is the 29 in modulo 26? Yes, answer. Yes, that's great. So you have to use C instead of the Z in this case. If it is bigger than, that's why we use modulo 26, which is the number of the letters in our alphabet, in English alphabet, of course. So if the K is here, we have to use P minus 7, which in order to decryption, because we use P plus 7 in order to encryption. That's why now we are going to use -7, which is, let us do it here, L E W L Y P L U J L P Z, and it continues. I'm not going to do each of them. So the L equals 12, and E equals 0.5, and W equals 23, and L 12, and Y is 25, and P equals 16, and L is 12, and U equals 21, and J equals 10, and L equals 12. And what is P? Equals 16, and Z equals 26, and H equals 8. So you can do the rest of them, which is very easy. So that's why I do not want to lose so much time here. So 12 minus 7, which is 5. 5 minus 7, it will be -2, minus 0.2. And 53 minus 7, it will be 16. It will be 5, it will be 7, so 18. And it will be, we're going to make it 7, yes, 0, 9, 0, 5, and 7, it will be 14, it will be 0, 3, and it will be 0, 5, it will be 0, 9, 19, and 1, and it continues. So for the first one, 0, 5, it will be E. So -2, how we are going to find the -2? So -2 in, what is the modulo 26 in, if it is -2? It means that we are going to add 26 to here. It will be 24, right? So I can say that it is 24. What is 24? It is X. So 16, it is P. It is E, which is R. and 9, which is I, and E, and 14 it is N, and it is C, and it is E. Experience, it means experience. 9 is I, 19 it is S. Experience is, which is 1, which is A. Experience is a something. What it is. You are going to just solve this one. Okay? This is too easy. That's why I'm going to just go and jump to other topics. So at first, we are going to see RSA crypto system, which is uh, commonly used by the cybersecurity systems, especially in 1976. There are three researchers in MIT, which are Ronald Rivest and Ali Shamir and Leonard Adelman. They introduced to the world a public key crypto system, which is RSA crypto system. It says, yeah, thank you, Oz. It goes like that. So in this system, each individual has an encryption key. The encryption key, we are going to see that as here, which is seen. This will be an, so it means that we will have an encryption key. Encryption key, we are going to use that one, which is E and capital N. I'm going to use actually, because I do not want to make it confusion for you. This is the capital N, and the capital N should be, this capital N should be multiplication of prime numbers. It has to be a multiplication of two prime numbers, which it says the modulus is the product of the two large prime P and Q, say with 200 digits each. It means that we are going to find, actually in the system, in the RSA system, we use very highly developed computers and highly developed servers in order to produce a prime number, which is 200 digits of each. And now the N is a product of the large prime numbers and P and Q, and they each of them have 200 digits, and an exponent E that is relatively prime to here. I'm going to explain what it means actually, but it means that now, of course, we are going to see a very basic steps. Okay, in real life, they do not use what we are going to use, because we are going to use a smaller or very small prime numbers. But in fact, in the system, they have to use very, very large prime numbers in order to use that system efficiently. That's why we are going to use, and we are going to only consider about the very small prime numbers, like 2 or 3, like 7 or 4, 13, something else, okay? Because it has to be uh, solved by the calculator, because your calculator has no, or has very limited uh, server and limited memory and limited showing case it has. So that's why we are going to use a bit smaller, or the basic uh, template of this RSA system, let me say. Okay, now which means now we have an encryption key, which is E and N. So we can rewrite here encryption key, it has to be E and N, and we know that N should be multiplication of two prime numbers, and E has to be relatively prime to P minus 1 multiply Q minus 1. We call it as Euler totant. Okay, I'm going to explain what it is. and E has to be co-prime with Euler total, which means there should be nothing or any kind of integer that also divisible by E and divisible by T. It means that if we are trying to, it means GCD, greatest common divisor of E and Euler twotant, should be only 1. Okay, so there should be no any common divisor or common factors between the Euler twotant and E. This is one of our first rule, which is very important. Okay, so to produce a usable K, two large primes must be found. This can be done quickly on computer using probabilistic probability test referred to earlier in this place in this lecture. However, the production or product of the primes with approximately 400 digits cannot be, as far as in currently now, be factored in a reasonable length of the time. So that's why we are going to use a very small sample of this system. And also the RSA crypto system encrypts blocks of characters into blocks of characters. It is block cipher actually, but let me explain you if I have a space here. Let me check. Okay, I'm going to use that place, but let me say here, for example, if you want to say love you much, let me say. Okay, now actually in the RSA crypto system, it uses as, for example, what is L? To quickly, L is 12. Oops. F is 12 and O it is 15, and let me say this is 22 and this is 05. Now we are going to use the RSA algorithm. We are going to apply for each letters one by one. Why? Because I'm going to explain. But in RSA crypto system, it uses that number, which is, this is only one number, which means it is 12,152,205. So they uses as, for example, 15 power of that number. Okay, let me rewrite here, for example. This is the power of the 15. And it uses such like this or kind of this crypto system actually. And also this one is 1215. So that's why we cannot use or we cannot solve any problem by using this one, only by using our calculator. And also our computers may not solve that problem too. So that's why, because it will take so much time, that's why you are going to use only the sample, and also you are going to understand what is the philosophy of the RSA algorithm and what is the RSA crypto system actually work. Okay, so let us continue. For example, encrypt the message, which is a stop, using the RSA crypto system with the key. Key is given here. And now what is the first thing that we have to do is, now it is the 13. 13 means that it is crypto system with the key. The key is given as, we are going to use encryption. So that key has to be encryption or encryption key, or we can call it as public key. Public key and encryption key is the same, and which is 13 and 2537, which is, this one is E and this one is n. How you understand that one is n? Because the e generally is smaller than the n, because n is multiplication of two different prime numbers. For example, it is given already in our question. It is the prime numbers, which are the p equals 43 and q equals 50, 59. So p equals 43 and q equals 59. So for example, in this example, what the crypto system or RSA works, or how it works actually, at first it tries to write stop as, for example, which is s is 19. Let me rewrite again. And t is 20, and o equals 15, and p equals 16. Now, how it uses s, for example, for this one, for the first one, it uses 19 and 20 power of what is our public key, which is 13. We are going to use 13 in modulo what is our n, which is 2537. Actually, this one is the how the real, or the in real life RSA uh, crypto system works. Okay, but in this case, for example, what is the result? We are going to check if you have to time, and if you have, for example, let me check if our calculator on my computer, not my calculator, using the hand, do it if it works correct or not. Yes, in this case, it says that the result is, and this is the encrypted way. Okay, now we are going to use for this one, for example, 15 and 16 power of 13 again in modulo 2537, and let us do this one too. 24 and 98. So we are going to check what is the 13. 13 equals m. And what is the 67? 67 for the modulo 26, and it is 2. So it will be b. And what is the 15? For example, 24. 24 is x. And what is the 98? 98 modulo 26, it is 20, so the 20 is t. This is the ciphered text in RSA algorithm. But this is what this is not the we are going to use. Okay, this is the how the RSA algorithm actually uses. But of course, instead of the 13, they have to use very big prime numbers, and also for the n it might be approximately 400 digits number, because each of the p and q has 200 digits, and they are also prime numbers. Okay, let's continue what or how or which way you are going to apply in order to find the RSA algorithm by using our handy calculator. So what are the factors? For example, factors of these very huge or large numbers, we have to use software, but in our cases, in our lectures, in our final exam, for example, we cannot have any We don't have any software that is specialized for the RSA algorithm. That's why we are going to use and this way the steps and use our calculators in order to solve the problem. So we have 6 step, let us say, actually 5 step, we can say 2. At first, we are going to choose, let me say, there's a word. I'm going to use I'm going to explain and show you some exercises too. But if a word, let me say this word is given in order to encrypt, if it is asked you to encrypt that message, the message, for example, what you have to use or have to follow in the first step, you have to choose two very large prime numbers, which is p and q, but we are not going to use large numbers. We are going to choose two prime numbers which are a bit smaller, and the n, as you remember, that this is our public key. For public key, the n is e, which is encryption key, and n, the n equals p multiplied by q. And also we have p minus 2 and multiplied by q minus 1, and p minus 1 multiplied by q minus 1, which is called Euler totent. We call it, or we show it as this one, and also p minus 1 multiplied q minus 1. And choosing two numbers, which is e, we are going to choose e. And as you remember that E should be co-prime with the N, and also E should be, let me write here. Let me finish this one at first, then I'm going to write these constraints. So we are going to choose E and D. What are they? You are going to choose. And for public key, we are going to publish E and E, this one, and this will be used for public key. And we are going to use the D as a secret, and we only share this private key with our friends. Okay, for example, when you just try to write a message, for example, from the WhatsApp, it says that in the head of the screen, which is the warning to the users that these messages are encrypted from end to end. This means that they use they use encrypto system too. Or what, for example, when you just register to a website, for example, when you just type into the password part as your password, but your password is hashed too, which is a kind of a cryptography as well. So the owner of the website may not know, and also generally they do not know what your password actually is, because it is automatically turned over to the hash. So you are going to see what they are actually. That's why we use the crypto system very frequently in our real life. So let me do an summary, a summary. Let me say this, and summary and the basic steps. At first, we are going to choose two prime numbers, but they will be not very large. They will not very large prime numbers. And these numbers are P and Q. As far as we know, multiplication of P and Q equals N. And P minus 1 multiply Q minus 1 equals Euler totent. And now we are going to decide what are the E and D should be. So the E, there are constraints. E has to be co-prime with N and Euler totent. This is very important. And also we are going to see the D. How we are going to find the D? D X is modulo Euler totent. So here it is very easy to understand what is the D is here. It is the inverse of E in modulo Euler totant. Okay, so this is very important. When you decide the E, then you have to find what is the D, because it is the private key we are going to use. So here we can say that for public key, let me write in other color. For public key, we are going to use E and N. For private key, we are going to use D and N. Okay, and also this is very important as well. So if any word is given to you, and if it is asked you to encrypt this message, you have to choose two prime number at first. Let us say which one. The first one is P and the other one is the Q. And the multiplication of these two prime numbers will be N, and the P minus 1 multiplied by the Q minus 1 will be the Euler totant. And this Euler totant is important for us. Why? Because this E has to be co-prime with the N and Euler totant at first. And in order to find the D, or the determinant of the value of the D, we have to find the inverse of E in modulo Euler totant. And then you can say that, or you can find what the public key is and what the private key is. Okay, let's do some exercises and we will see what actually it is. So, for example, let us do one example. Let me change the color. Okay. If the public key is equals 5 and 14, and the secret message, or actually not the secret message, at first let us choose for from the beginning. Actually, let me do this from the beginning. Okay, let us try to just encrypt a message of very small numbers, or let me say this is only the one letter, which is B. Okay, I choose B, and it is 02, which is the number of the letter. Okay, what is our first step? We are going to choose two prime numbers. I'm going to choose, for example, 2, and for Q is 7. You can change it if you wish, it doesn't matter. But in the end, you have to follow in the same steps, and you have to control what are your results, and you have to control your and also you have to control your solution by encryption and also decryption too. It has to work for both sides. Okay, for the first one, I choose my prime numbers. For the second step, I'm going to define what is the N. N equals multiplication of the P and Q, which is 2 multiplied by 7, which is 14. So the N equals 14. So for the first step, we are going to find what is the Euler totant, right? So P minus 1 multiply Q minus 1, which is 2 here, as you know, is 2, and this one is 7. So in the end, we can say that it is 1 multiplied by 6, which is 6. Then You can say that Euler total equals 6. So we find these important variables. Now we are going to find what is the E. So for the first step, determine E. So E has to be coprime. E has to be coprime with 14 and 6, right? Because 14 is n and 6 equals to Euler totant. So it has to be coprime with this one. And also, as you are n1 for the fifth step, you are going to determine D. And as we remember that E multiplied by D should be 1 in modulo Euler totant. So E multiplied by D equals 1 in modulo 6. Here we can say that E has to be greater or equal to 0 and has to be smaller than the 6. So E has to be between this is E, by the way. Okay, and 6. And also it has to be coprime with 14 and 6. Okay, now what are the possibilities? For example, 0, 1, 2, 3, 4, and 5. So it cannot be 0 or 1 because we are going to eliminate these two. And let us check, for example, 2 can divide 6 and 14. That's why 2 cannot be. And also inside of the 4 we have 2. That's why we just eliminate this 2 to 4 as well. And 3 can divide 6. That's why we eliminate the 3. And the only one, which is the 5, which is, we can say that E equals 5. Did you understand how we found the E till now? That's great. Now we know that the E equals 5, and we are trying to find D, which is 1 in modulo 6. So we know that D has to be between as E, which is 6. So what should be the D is here? D should be equals 0, 1, 2, 3, 4, and 5. Yes, it cannot be 0 and 1. And it can, if it is 2, it will be 10, and remainder will be 4. If it is 3, it will be 15, and the remainder will be 3. And it will be 4, it will be 20, and the remainder will be 2. And if it is 5 multiplied by 5 is 25, and the remainder will be 1. Yes, so we can say that it is 5. So D equals 5. But now we get it as E equals 5 and D equals 5 too. So it is better to make, if you can use this one too, okay, by the way, but all the process will not change and you cannot see the differences. So I'm going to write as you know, it will be the same. D5 equals 11. Why? I just added 6. Okay, I'm going to use 11 in order to D because it is the same. Okay, just I'm going to show the difference between E and D. That's why I choose 11. Okay, I may choose 5 too, but the further examples and further exercises, you are going to see different questions too. Okay, now we have public key here, public key, which is 5, and what is the n? It is 14. And we have also private key, which is 11 and 14. We found this one, and now we are trying to encrypt B, for example. Let us do here B equals 0, 2, and our public key equals 5 and 14, which is E and which is N, and this is public key. And also we have a private key that will be shared with our close friends, let's say, is 11 and 14. So how we use or how we encrypt these messages or these letters by using the public key and the private key too. So for example, what we are going to do is this is E equals B equals 2 power of E we are going to use in order to encryption, and what is the result in modulo n. Okay, so here 2 power of 5 equals what in modulo 14. So the 2 power of 5, it will be 32, and if you just, it is very easy actually, 32, and if you divide it by the 14, the remainder will be what? Yes, it is 4. The encryption, so the B is 2, C is 0, 3, and D is 0, 4, and now it is 4. So we can say that the encrypted message for B, it is D. Okay, instead of B we have to write D, or this is the D is 4. We are going to decrypt what is the X in modulo n. It is the same, so 4 power of 11, what is the X in modulo 14? So we are going to calculate what the X is. So 4 power of 11, it is 4,194,304 modulo 14. Remainder will be 2, which means decrypted message for D, it is B. Okay, so of course when you find the encrypted message, and if you decrypt that encrypted message, you have to get the original message, of course. So in original message, in our case, it is B. Is there a problem? Is there a question? Now I'm going to share with you some other examples. Okay, now we have seen this one. Okay, I'm going to skip this one too. Okay, now we have now you can see, right? Clearly, I guess. But not this one, but I'm going to solve this one, but after that one I will arrange the notes. So here we are going to encrypt the message love using the RSA crypto system with a public key, which is 5 and 14, and D can be 5 between the 5 and 17. So there is a constraint in order to choose the D. So actually we don't need to decryption because it says that encrypt the message. It says that encrypt the message. We don't have to use, or we don't have to find what the D is, but it is also asked in this question. That's why we are going to use. So what is, at first, we have to follow our steps, okay? The first step, we are going to determine what the P and Q is. The P, it is, the N is our second step, which is N. N equals 14, and this 14 should be multiplication two prime numbers, which is P2 and Q equals 7. So we can say that it is PQ and Q equals 7. So for the third step, P, we are going to find the Euler totant, which is P minus 1 multiply the Q minus 1, which is 6, which is Euler totant. And for the fourth step, as far as we know, in previous example, we have used the same public key. That's why we use what actually E equals 5, which is here is E, and this one is N. So E equals 5, and the D equals, they are the same. That's why D equals 11, because it has to be between the 5 and 17. It means that D has to be 11. So now, love, what is the L here? So let us love, or right here. Okay, for the L equals 12, and O equals 15, which is given here, and V equals 22, and E equals 5. We are going to encrypt the message, so we have to use encryption key here, okay, which is 5 power of 5 and equals what in, or you can say x1, x2, x3, and x4 in modulo n. What is our n? Is 14. So it will be the same for 14 and mod 14 and mod 14 too. So let us use our calculator, and modulo 14, it will be 10. This one, let me say that is x1 equals 10 and x2 equals 15 power of 5, and in modulo 14 the result will be 1. For x3, 22 power of 5, and modulo 14, what's the remainder? Remainder is 8. For the x4 equals 5 power of 5 in modulo 14. The result is 3. So what are these letters in our alphabet? For the 10, it is J. For the 1, it is A. For 8, it is H. For 3, it is C. So here is J, A, H, and C. It is encrypted message of love. Okay, this is the answer. And we found the D. And also we encrypt the message of the love as here. If we want to decrypt this message, for example, if I have, okay, I have a place here, JAHC, and we know the public key, but we do not use this public key. And also we have a private key. We are going to use the private key because it is used for the decryption, which is 11 and 14. So the J equals 10 power of 11, and A, it is 1. And if you take the A as only 1, you cannot change A. Okay. Yes, of course we can take it as 3 and 5 also, but it will be changed. The encryption or decrypted or encrypted message will be changed. So you have to just try to do it by yourself. I'm going to explain and I'm going to share with you another examples too. But here, for example, if we have JAHC, this is the private key. But in your key, in your word, if there is an A, you shouldn't use 1, because power of something else, power of 1 or whatever the number is, the result will be 1. So you cannot encrypt the 1 according to your public key or according to your private key too. So in this case, you have to take it as 27, which is 1 in modulo 26. The 26 is the number of the letters. Okay, that's why we are going to use as 27 power of 11. So for the H, we are going to use it as 0.8 power of 11. And also we have C, which is 0.3 power of 11. And what is the result of these ones in modulo 14? Now, for example, x1 has to be L, but let us check if it is really L or not. Power of 11, and the remainder will be 12, and it is actually L, which is here. So in the x2, it equals 21 power of 11, so 27 power of 11, and in mode 14, it is what it is. Let me check again. And modulo 14, it is 15, it is low. So it has to be the same as the result as an law. What was the, yes, it is law. So I'm going to stop the recording. I'm going to give you some other examples too.